Training a frontier AI model today requires tens of thousands of AI accelerators running continuously for weeks. Not hours, not days. Weeks of uninterrupted operation. A single full training run can consume hundreds of megawatt hours of electricity, comparable to the energy usage of thousands of homes over the same period. Depending on scale and efficiency, the cost of one run can range from tens of millions to well over $100 million, before inference, retries, or fine-tuning are even considered. This is the physical reality shaping the next phase of the AI race, and it's why the conversation has quietly shifted away from models and toward machines. Because the real bottleneck in AI right now isn't intelligence, it's compute. By the end of this video, you'll see why two stories that look separate, the escalating AI chip battle and the rapid infrastructure expansion by xAI, are actually part of the same struggle for control. For the last few years, AI progress looked like a software story. More parameters, new architectures, smarter reasoning, faster demos. But behind the scenes, a harsher constraint emerged. Every increase in model capability multiplies infrastructure pressure. Larger models demand more memory bandwidth. Scaling requires faster interconnects between chips. Power density rises, making cooling exponentially harder. At scale, these constraints don't grow linearly, they compound. This is where many AI labs quietly hit a wall. Some teams have models ready to train, but no available accelerators. Others secure hardware but can't get enough power allocated in time. In several cases, promising research stalls not because the ideas failed, but because the infrastructure timeline slipped by months. This is the part of the AI race most people never see, and it's why the battle has moved from algorithms to hardware. For years, NVIDIA became the default supplier for large-scale AI compute, not just because its chips were powerful, but because they came with a mature software ecosystem, predictable performance under extreme workloads, and early availability when AI demand exploded. That early advantage created momentum. Momentum created dependency, and dependency created pricing power. But dominance has a cost. Large buyers increasingly want alternatives, not necessarily because NVIDIA's hardware is bad, but because dependence is expensive and risky. If one supplier controls too much of the stack, negotiating leverage disappears. This is where challengers enter. AMD's strategy isn't about beating NVIDIA on peak benchmarks. It's about economics, performance per watt, cost per unit at scale. For buyers deploying tens of thousands of accelerators, a small efficiency gain can mean millions saved every month. Intel's position is more existential. AI isn't just another market. Losing relevance in AI hardware risks losing relevance in data centers entirely. Its comeback efforts reflect urgency, not confidence, a high-risk attempt to stay in the game. Broadcom is taking a quieter but powerful approach. Instead of competing in general-purpose AI chips, it designs custom accelerators for hyperscalers that want chips optimized for specific workloads. Fewer customers, but deeper lock-in. Lower flexibility, but tighter control. This isn't a race to build the best chip. It's a negotiation over who controls the economics of AI. Chip design decisions determine how large a model can be before memory becomes a bottleneck, how efficiently thousands of chips can communicate, how much power a data center can support, how expensive inference becomes at scale. Now consider this from the buyer's perspective. If you're a cloud provider or AI lab CTO ordering 10,000 accelerators, you're not asking which chip is theoretically fastest. You're asking, can we get them on time? Can we power them for 5 years? Can we cool them without redesigning the building? Can we afford to run them continuously? Those answers matter more than benchmarks. And chips are only the first constraint. Once hardware is secured, it must be deployed. Modern AI data centers are not generic facilities. A single rack of accelerators can draw several times the power of a traditional server rack. Cooling systems must handle extreme heat density. Networking must move enormous volumes of data with minimal latency. Every expansion requires long-term power contracts, utility upgrades, permits, specialized construction, and months of coordination. Which leads to the next open loop. What breaks first when AI demand accelerates again? Chips, power, or physical space? Because delays here don't just slow progress, they decide who stays competitive. This is where xAI's expansion becomes critical. Acquiring additional buildings isn't a branding move. It's a bet that future AI progress will depend on having compute ready before it's needed. Training large models requires long, uninterrupted runs. Interruptions waste capital, delays compound. And if competitors scale faster, the gap can become permanent. But this bet carries risk. If demand shifts, if costs outpace revenue, or if competitors gain preferential access to infrastructure through cloud partnerships, those physical assets can turn into stranded capital. This is the trade-off defining the next phase of AI. The industry is starting to resemble capital-intensive sectors like energy or manufacturing. Upfront investment matters more than elegance. Access matters more than novelty. Timing matters more than perfection. This creates a sharp divide. Cloud-backed labs can absorb inefficiency while they experiment. Independent labs cannot. They must scale faster or disappear. And when companies lose this race, they rarely fail loudly. They downsize, they pivot, they get acquired, or they quietly fade as compute costs overtake their runway. This is the narrative layer most AI coverage misses. The chip battle and infrastructure race don't just decide winners. They decide who is allowed to remain in the game at all. As AI becomes embedded into products, services, and entire economies, compute stops being a technical detail. It becomes leverage. This is why 2026 matters. Not because AI will suddenly get smarter, but because by then, the critical decisions will already be locked in. Chip supply agreements, power access, physical capacity, and operational expertise. And that leads to the final open loop. What happens when chip supply itself becomes strategic, not just scarce? By the time the next major AI breakthrough arrives, the playing field may already be closed. So when you hear about new AI chips, quiet data center expansions, or massive capital spending without flashy demos, don't dismiss it as boring business news. Those aren't side stories. They are the story. Because in the next phase of AI, intelligence won't be scarce. Compute will. And the companies that control it won't just shape technology. They'll decide who gets to participate in it at all.